All right, let's dive in. Today, we're going to pull back the curtain on the language of computers. We're going to solve a really common mystery about your hard drive and even uncover a wild digital illusion that makes subtraction possible in the first place.
You know that feeling, right? You buy a shiny new 1 terabyte hard drive, you plug it into your computer, you get all excited, and then you see that you only have about 931 gigabytes of space. It happens to everyone. So where did all that storage just go?
Well, here's the good news. You haven't been ripped off. The space isn't actually missing. The whole issue is basically a translation problem. It turns out that hard drive manufacturers and your computer's operating system are speaking two completely different languages when it comes to numbers.
To really get to the bottom of this, we first need to understand how we, as humans, count versus how a computer does it. It all comes down to the number base.
So for us, our entire world revolves around denary, or base 10. It's just how we think. We have 10 digits, right? 0 through 9, and we use those 10 symbols to build every number imaginable. Each spot in a number is just a power of 10. Pretty straightforward.
Computers, though, they're much, much simpler. At their very core, they're just billions of tiny switches that can either be on or off. That's it. So their entire language is built on just two symbols, 1 for on and 0 for off. And each one of those ones or zeros is called a bit.
So how does a computer take a number that we understand, like 101, and translate it into its own language? Well, it's kind of like a little game of subtraction. The computer looks at 101 and says, what's the biggest power of 2 that can fit in here? That'd be 64. So it puts a 1 in the 64 spot. It subtracts that, leaving 37. Then it does it again with 37. The biggest power of 2 that fits is 32, so it puts a 1 there. It just keeps doing this, putting a 1 for every number that fits and a 0 for the ones it has to skip, until it gets all the way down to 0. And just like that, our 101 becomes a string of 1s and zeros.
Now you can probably see where this is going. Binary numbers can get ridiculously long really fast, and this creates a huge problem for the humans who actually have to work with them, which led to a pretty clever shortcut.
I mean, can you imagine trying to find a mistake in a computer program by just staring at a wall of thousands of ones and zeros? It would be an absolute nightmare. Programmers and engineers desperately needed a more compact, more human-friendly way to look at all this binary code. And the solution they came up with is actually pretty elegant. It's called hexadecimal. This is a base 16 system. It uses the 10 digits we already know, 0 through 9, and then it just adds the letters A through F to stand for the values 10 through 15. And here's why it's such a perfect shorthand for binary. This table is basically our Rosetta Stone. You can see that every single hexadecimal digit, from 0 all the way to F, matches up perfectly with a group of 4 binary digits. That 4-bit group is actually called a nibble, by the way. So a long, messy 8-bit number, like 101101111, can just be chopped in half, translated to B in 7, and shortened to just B7. Way easier for a person to read and remember. Okay, so we've got our human language, base 10. We've got the computer's native language, base 2. We now have all the pieces of the puzzle. Let's finally solve the mystery of that hard drive. And this is the crucial detail. When manufacturers advertise a 1 terabyte drive, they're using the simple, human-friendly base 10 system. To them, giga means a nice, clean 1 billion. But your computer has to operate in the binary world, where all the prefixes are based on powers of 2. So a kibibyte isn't 1,000 bytes, it's 1,024. And that tiny 24-byte difference might not seem like much, but it compounds like crazy as you scale up to mega, giga, and tera. So let's do the actual math. The manufacturer gives you exactly 1 trillion bytes. But when your computer reads that number, it doesn't divide by 1,000 to figure out the size, it divides by 1024. So you take that 1 trillion bytes, divide it by 1024, divide that by 1024 again, and then one more time, and what do you get? 931.3 gigabytes, which your computer just calls 931 gigabytes for short. Mystery solved. The storage was never missing, it was just lost in translation.
So why does this all matter? Well, for marketing hard drive space, using those nice round base 10 numbers is just simpler and, close enough. But for something super precise like your computer's RAM, there is absolutely no room for close enough. The system needs to know the exact number of bytes it has to work with, down to the last one. That's why RAM is always based on these precise binary units.
So, we've figured out how computers and humans translate big numbers. But that brings up another really interesting question. We know computers are built on simple circuits that are just really good at adding.
So, how in the world can they handle subtraction?
No, really, think about it. There isn't a physical minus switch inside a processor. So to perform a simple calculation like 7 minus 3, computers had to come up with a genius workaround. They asked, what if we could just represent -3 and then just add it to 7?
And that incredibly clever method is called 2's complement. It's the standard system that basically all modern computers use to represent both positive and negative numbers in a way that lets all the math work using the same simple addition circuits.
And the process itself is so simple, it almost feels like a magic trick. To get the negative version of a number, you start with its positive binary form. First, you flip all the bits. Every 0 becomes a 1, and every 1 becomes a 0. Then you just add 1 to that result. That's it. You've just created a negative number.
The secret that makes this whole thing work is how the computer treats that very first bit, the one all the way on the left. In the 2's complement system, that bit is given a negative value. So for an 8-bit number, its value isn't positive 128, it's negative 128. This one small, clever twist is what allows the entire system to work perfectly. And the benefits of doing it this way are huge. For the hardware engineers, it means they only have to design and build one simple, efficient circuit, an adder. That single circuit can now handle 5 plus 2, 5 minus 2, even -5 plus -2, all using the exact same logic. It makes the CPU design so much simpler and keeps all the math consistent. So, from missing gigabytes that were never actually missing, just translated differently, to subtraction, which turns out to be just an illusion of adding a negative number, it seems like our computers are just full of these clever tricks. It really makes you wonder, doesn't it? What other fundamental ideas are just elegant illusions hiding in the code? Thanks for joining me.